Dear students, in this video I am going to explain very important part in electrochemistry, and it is called Nernst equation. It is called Nernst equation. So it is basically a relationship between the electrode potential, standard electrode potential, gas constant, then temperature, concentration of electrolyte, etc. So first see or dependence of cell potential, dependence of cell potential on temperature, concentration, gas constant, etc. So it is a relationship between all this, and we have seen in the previous topic that it depends on basically the temperature also. So this is the exactness. E cell or E standard cell is equal to E right minus E left, but there is not the absolute accuracy. The reason behind that there is not absolute accuracy with this simple relationship, because it involves only the standard electrode potential. So that's why there is the requirement of Nernst equation. So Nernst equation, it is very simple relationship. See how it is. E cell is equal to E standard cell. This is there. Now then there is the H gas constant, absolute temperature, this N ln natural log. There will be concentration of metal, and here the aqueous solution. So this is the basic, or this is the original Nernst equation. And so here this is cell, it is the cell potential, or we say electrode potential. Then E naught cell, as you know, it is a standard electrode potential. Then R, it is gas constant, 3.14 joule per kilo per mole. Then T, absolute temperature. Then N, small n, it is the number of electrons involved in the reaction. Reaction means the chemical change, number of electrons. See, if we have like this, there is copper, and copper ions are getting the 2 electrons here. So there will be formation of copper solid. So here N will be equal to 1. This is the simple logic, the number of electrons involved in the equation, and more precisely in the balanced chemical equation. Then this F is Faraday's constant, and 96500 coulomb. 1 Faraday has this value 96500 coulombs. Then coming to this, now this MS, it is the concentration of metal, and concentration of metal by default we take as 1. This is the concentration of metal, or say molar concentration. And about this metal electrolyte, so this aqueous, it is the concentration or molar concentration of electrolyte. Now this last portion, this ln is called as natural log. So this ln, here I am writing ln x natural log, it is 2.303 log x. This is natural log. All the mathematical calculations, they basically involve this natural log, that is ln, and it is power x, it is power having x, and this, when it is converted into this log base 10, so we multiply by 2.303 as the conversion factor. So this is there. Now on putting the value, we'll get this all. How? See, I'm going to put all the values. So here, see, this is, E naught cell, then this gas constant 8.314 joule per Kelvin per mole, then temperature 298 Kelvin temperature, then this conversion factor 2.303, n, we have this n as standard value, and then 96500 coulombs, and here this ms, so it will be, it will be equal as it is this ms, and here this number of electrons equals. Now children, on multiplying all, we have some concrete formula to use comprehensively as a single tool for calculating standard electrode potential. Now here we can keep it here 1, because for solids concentration is taken to be 1. So on multiplying all, this is the, so here we have on multiplication all 0.0591 upon n. This we have completely homogenized this, and then it will be log 1 upon this equals. So this is the point. Or we may further simplify here, E naught standard minus 0.0591 upon n log. So it will be plus here, and here it will be written as this. So this is the final, and this is the workable final or workable Nernst equation to be used comprehensively, and the point is there. Actually, in some cases where the number of ions are unequal, we'll see in next part. See how we will apply the Nernst equation in the Daniell cell. See how. So for Daniell cell, and for Daniell cell we write this equation, overall equation or cell equation. See how we write here zinc solid, then zinc ions, then salt bridge, then copper ions, and whatever you write the concentration, let it be x, here let it be x. So then copper solid, and this is our basic E standard cell is equal to E right minus E left. It will remain as it is. It will remain as it is. Now we write the Nernst equation for single electrode. So how we write down that E zinc ions is equal to E naught zinc ions minus, just write the concrete outcome. So 0.0591 591 upon n log. You write down plus, and then concentration of zinc ions. Then for the other point, that for the copper, here we write, and so E0 copper ions plus 0.0591, here 1 also, on n log, then copper ions. Now we'll put all the values here. We'll put all the values here as it is, nothing. On putting all the values here, so we'll get the complete value. See how. Now I am in the last portion of this calculation part. So we'll use this formula as basic one. This is the basic formula. The point is there's the dependence of the cell potential on the different parameters. So we'll apply here. See how this E, then copper, E zinc, it will remain as it is. It will remain as it is. What it is incorporated here, what it is used here. And so it is again here E standard copper ions minus this zinc and zinc ions. So again we'll put the values here. No need, just I am writing the how we come to the absolute conclusion. So on putting all the values, we have the following point. So here we'll have this E cell, this cell potential. This is the cell potential, and so we'll have this cell potential and is equal to E standard from this two, and then minus 0.0591 upon n log. There will be concentration of zinc ions, concentration of copper ions. So here this is the generalized form. This is the generalized form of the Nernst equation. Now further generalization, further simplification. This or this I am writing for any equation, any cell. So here E0 minus 0.0591 upon n log. Now here in this place we write down the anode, and here we write down the cathode. This is there. Now one more point. When the number of electrons are not same, so what to do? Number of electrons are not same, so what to do? So simply we change the concentration by suitable coefficient. See how. Suppose we have a cell in which the number of electrons are not same. So what to do? And so I am writing that here we have this nickel solid and nickel aqueous salt bridge. Here we have silver ions aqueous, and then we'll have the silver solid. So we have to multiply here. See, the number of electrons here are 2, so we'll put here 2. We'll put here 2. And so actually in this E cell, so E cell will be equal to, now so this is the anodic portion, this is the cathodic portion, again applying the same. Just so here we write down A standard, this cell, that is Ag Ag minus standard nickel. So it is standard or 0.0591 upon 2 here, because here I have put 2 to multiply the number of electrons. Then here log, and on this point there is the anodic portion, anodic half shell. So here we'll write in nickel 2 plus, and here silver. But children, here charges are not same. Here we have put 2. So now we'll put 2 here. So this is very important part. In case the two ions are unequal, then what to do? We'll put suitable coefficient as per the thing. So just summary, in case of ions having unequal charges, suitable coefficient is used to balance the charges. So this is all about the Nernst equation and how it is affected. Temperature has very important role. Then gas constant. So all this. So this is all about the Nernst equation.